diagram, okay, we generally label this as real and this as imaginary. Alright, some of you ask whether is it possible to label this as real of z, imaginary part of z. The answer yes and no. When do you do that? You can do that if you are only indicating one complex number. That's probably, maybe you're just going to indicate maybe z equals to 2 plus 3i. And this is your complex number. Okay, if that's you're only drawing representing one complex number, that is fine. But if you're representing 2, for instance z1, z2, maybe 4 plus 7i, then it's advisable that you don't use this. You don't use the z. Okay, try to take it away. Okay, second question, someone asked argument of z. Okay, why is this between pi and negative pi? Honestly, I went to ask all the math teachers. Okay, there's no answer for this. It's really definition. Okay, there's no proof for it. It's really definition. Okay, but I think it's a good question. If you're thinking why, I think you're doing very well as a student because you really question the source of things. Okay, okay. What else? Okay, some of you do this. Real, imaginary, 2 plus 3i. Okay, and you put 2 here. Okay, when you went to calculate your modulus, what you did is you actually you did this. Okay, is it correct? Answer is no. Why? Because when we are calculating the modulus, we only take the real and the imaginary parts. Okay, the parts. We do not take the I. So given x plus iy, right? When we calculate the modulus, we only take x, we only take y. We do not take the iy. I by default is already when we put it on the y-axis, it's already seen as a unit. It's a unit for the imaginary part. So when we're calculating, we should take away the I. Okay, it should just be 2 square plus 3 square square root. That should be your modulus, your magnitude of your complex number. Clear? Clear, okay, okay, another thing that I forgot to emphasize, okay, last time I told you, we generally try to use dotted lines to represent a complex number, okay, then I went back to think, how is possible to classify it in a simple way so that all of you can get the argument fast, can talk about it, okay, so maybe first, just remember, if it's in the first, but if it's in the third and fourth quadrant, you will go clockwise. Okay, you will go clockwise. This is clockwise, clockwise, anti-clockwise, anti-clockwise. Okay, Ken, how about this? Easier to understand? Just remember, first and second quadrant is always anti-clockwise, third and fourth is clockwise. Okay, Ken, I mean, that should give you an idea. Most important, if you are going to, today you'll be learning the polar form, and you need to be able to find the argument as well as the modulus correctly. Okay, cannot find correctly, then die in mampus. Okay, next one. So going back to question, this is where we stopped the last time round, okay? Right, vector representation of complex numbers. Okay, if you want to do, use vectors to represent complex numbers. Can we do that? Yes, only for certain parts. Okay, there is we only use the position vectors. We only use the position vectors. Shh, don't talk. Okay, no matter how handsome the guy is, don't talk until the salary shirt. Okay? Okay. Oh, is it? Did I? Okay. I step on the sheet. Okay. Okay, sorry, joking. Don't get angry, don't complain about me to your parents. Okay. Question 13. Vectors representation, you can use parallelogram law of addition. Parallelogram law of addition tells you this is A, this is B, right? Then this will just be A plus B, where A plus B will be the diagonal of the parallelogram formed by A and B. Okay, you can do that. How about, so here, right, you can see that Z1 and Z2, this is a Z1 and this is a Z2. Z1 and Z2, it can also be represented in this form. Okay, can I ask you in an exam question, maybe I can ask you to indicate Z1 plus Z2 in the diagram? Yeah, but those of you who talk to your seniors, the geometrical reflection, okay, what happens when we multiply I to the complex numbers. All these are no longer in your syllabus, so you don't have to worry. No? There are some parts here that your senior study or you need to study. Okay, it's very simplified. Okay, how about Z1 minus Z2? Okay, so if you were to think about okay. Okay, let's say if this is my Z2, right? Okay, so similarly, if we think about vectors, right, our Z2 so-called is pointing in this direction. We can say, okay, let's say I just use Z1. If Z1 is pointing in this direction, can I say negative of Z1 is also pointing in this direction? Can, right? So similarly, if I were to look at this, so-called form a parallelogram, okay, then what would this, let me use another color. What should I use? Okay, orange. Blue, okay. Blue, okay. So this will be what will this vector be? This will just be negative for Z1 plus Z2, right? Correct? Otherwise, you can also say this is just a Z2 minus Z1. So this is also how you represent subtraction of complex numbers. Okay? So my own mistake, I shouldn't have used, I try not to use arrow, I try to use, okay, dotted line. Okay? So this is how you represent. Can you see? Oh, shucks. Okay. Okay, so this is how you can represent a subtraction of complex numbers. But bear in mind one thing. Only use only use position vector. Okay? Only use position vectors. Do not use direction vector. Do not use displacement vectors. They don't mean anything in complex numbers. Okay? Only use position vectors. Clear? Okay, okay, then next. Okay, then this part. Okay. Question 4. Question 14. Okay, I believe this is empty in your student's copy, right? Okay, so just give me about maybe 2 minutes. Help me to draw out very quickly. Okay, what is Z and Z asterisk? Okay, draw out one complex number and its conjugate. Okay, so just take note of this. Okay, don't draw in the wrong quadrant. X plus iy, x and y are greater than 0. I hope by now you're comfortable that you remember that you label your Argand diagram properly, real and imaginary. Don't put Z, okay? X and Y are positive, so you are looking at the first quadrant. Alright, you draw a dotted line sincerely, you don't draw arrow. You can put X comma Y. Okay, just put if you want, let's put it clearly. Z equals to X plus IY. Okay? Then where is Z asterisk? Z asterisk will just be Z minus IY. So Z asterisk from the side, you know, is X minus IY. Where will it be? If this is Y, so you observe, right? This is the X. This is Y, right? Correct? Because they are actually just in the sense, your Cartesian coordinates. Okay? So we will extend the negative y-axis. Right? This will just be the green line, the green dotted line. This will just be Z asterisk equals to X minus IY. Okay? You can see that the X coordinate is the same. I used yellow. Okay? This is negative y. Okay? So this will be your conjugate. This will be how your conjugate looks like on the Argand diagram. And if I were to show you, right, if this is the argument of Z, okay, and can I say this is the argument of Z asterisk? Can, right? Are you able to draw a relationship between the argument of Z and the argument of Z asterisk? Okay, relationship. Any relationship? Can you see how they're related? Are you able to see? Okay, so in general, in general, it's always true that your argument of z, okay, is actually the negative of the argument of your z asterisk. Okay, regardless of where we put the negative sign. In your notes, they put a negative sign on the other side. Okay, so you can see that, for example, if this is pi over 6, and then this will just be negative pi over 6. Okay, so you can see that the arguments are the negative of each other. Okay, you can go back and try. So I will say, hey, but this is the first and fourth quadrant. How about if I try getting my argument to be here? Let's say if this is my argument of z. Okay, will this also be the argument of z asterisk? Okay, you can go back and try this. Okay, so you can go back and try this. Okay, but in general, it's the same. It's the same. Okay, they're just the negative of each other. Okay? So this is how it looks like. No one copying, so I assume you all know. Okay. Oh, someone's copying. Sorry. Okay, one good habit that you all have. Okay, I want you to know. Okay, try to do this. Okay, I mean not try. You must. Always have the habit of doing this. You draw the arrow. Okay, draw the arrow. Draw the arrow. It will help you to recognize your argument. So it means that whenever you state your argument, please draw the arrow. Okay, so you notice I always do this. Okay, you draw the complex number and you draw the arrow. There must be an arrow. Okay, there must be an arrow. I say again, there must be an arrow. I say one more time, there must be an arrow. Okay. Presentation, you all know, presentation sounds very irritating. You all lose 1 mark because presentation, all this very poor thing. So don't let it go to waste, okay? Don't let your hard work go to waste. Or there must be an arrow. Kai Heng, what did I say? Very good. Pointing to where? Pointing to where? Stop touching your chest. Okay, pay attention. Okay? So in general, I've talked about this. They are just reflection in the real axis. Okay, so you can see in a sense, it's like in the past we talked about this is a rotation of like 90 degrees, okay, but we don't see this anymore. It's no longer in your syllabus. Okay, the geometrical effect, we no longer discuss this. Your seniors they do, but not for us. Okay, this one I've talked about it. This one okay? Can, right? Can, comfortable, right? So it's just like algebraic manipulation. Okay. Next one. Okay, this will be the last part, so quite easy, very fast. Okay, how do we convert a complex number? How do we convert a complex number from one of the following forms to another? That we have 3 forms. There are in total 3 forms that you need to know for complex number. Not constant form, not information form, but there are 3 forms for complex number. Cartesian, okay, polar, and exponential. So today, after you walk out from this LP, you must be able to identify or recognize what are the forms of a complex number. Okay, stop talking, okay, listen to me. Okay? Next, okay, how do we multiply and divide 2 complex numbers given that in another form? In the Cartesian form, we know, right? It's just in the Cartesian form, x plus iy1, and I ask you to do x2 plus iy2. Okay, this one you can do, right? Okay, so now given that third last row, the 2 girls are in the center. Okay, please look. Stop chit chatting. Okay. Otherwise, later you can't share your gossip with me. I'll record it here. They'll send to HOD. Joking. But okay, pay attention to it. Okay, I'll appeal to your good will. Yeah. How do we multiply or do arithmetic operations, 2 complex numbers in polar exponential form? Also, how do we represent it in the Argand diagram? Okay, so this will be the last part of complex numbers. Okay, so look forward to it. It's so exciting. Okay, in the past, okay, let me just ask you. Okay, let's just try this for fun. Okay, now we know that there's something called the Argand diagram. There's a real, there's an imaginary part. Okay, then I ask you to do this. I give you this complex number. I don't know what's the coordinate, but then I tell you, okay, then this argument of this complex number is Initial you again. Tutorial you talk, lecture you talk. Stop talking, understand or not? Understand? Slap you then you know. Okay, so here, right, let's say if I give you this number, nice one, okay, you see, x is greater than 0, y is greater than 0. The argument is pi over 6. Okay, one more thing. Argument in complex number, we only use radian mode. We don't use degree. Okay, so when do you really use degree? Maybe your vectors law, correct? So what I do is every time, if I go exam, I bring two calculators. The scientific one, I put in degree mode. The TI-84, I put in radian mode. Because everything is in radian. Calculus is also radian. Or complex number also radian. Okay? So put it in, this is always in radian. Alright? Given this complex number, where the argument is pi over 6, are you all able to suggest to me what could be a possible x and y? Okay? So go back to your GH3 days when you learn special angles, right? Right? Pi over 6 is the same as 30 degrees. Okay, just give you 1 minute to think about this. Give me a possible x and y. Okay? You don't have to tell me, you can discuss with your friends. Okay? A possible x and y. Okay, my example is it can be square root 3 plus I. Is that okay? Is that okay? Can, right? Can, right? Okay, but one thing interesting you notice is this. Okay? One thing, okay, so you see actually from here, given the, don't need to take photo, I can send you all the clip later on. I record, I send you all, don't worry. So you can watch it 1,000 times, midnight you can watch also. I'll be talking to you in midnight, okay? So, the one thing you notice is that actually, right, somehow, if I give you a complex number, it's possible, if I give you a complex number and I give you an argument, it's possible to come up with another form of the number, okay? And I'm going to introduce to you the first one, which is the polar form. Given this is real, this is the imaginary part, and this is x and y. Okay, let's say for mod z, I call this r. Okay, I call this r. Okay, this part is r. This part will be y, right? This part will be x, right? In a sense, there's a right angle triangle here. Okay? Shh, follow me. Okay? You don't pay attention, you'll be lost. Okay, so I really need you to follow me. Sincerely, honestly, I don't want to scold you, but I think I don't want to point you out because I respect you. Okay, but so behave. Okay, so can I say this is theta? Okay, mod of z is equals to r. This is the modulus that we were learning last lesson. The argument that we were learning last lesson, I call it theta. Can you all see this? It's all okay, right? Okay, right? Okay. So, can you all see this? Okay, now let's look at this triangle. Okay, let's look at this triangle. Okay, I can say using Picasso, right? Cosine theta is equals to adjacent over hypotenuse, correct? Because this is the adjacent, this is the hypotenuse. Can ma? Can ma? Boleh? Okay. So if I do this one, can I say x is equals to r cos theta? Yes, how? Okay, very good. Similarly, using Picasso, sin theta is equals to y over r, right? Is equals to y over r, right? So I can say that y is equals to r sin theta. Okay, easy, right? Once you actually, if anybody asks you to prove, you can prove it easily, huh? But what does this tell you? This actually gives you a new form of the complex number. Okay, remember earlier on, 1 week or 2 weeks ago, we were studying this, right? Z equals to x plus I, y, right? Okay, so we call this the Cartesian form or the rectangular coordinates, okay? This, can you say that now, this x that we have can also be written in this form? It's wrong. Can also be written in, I draw a longer arrow, can also be written in this form. Can we also say that the y can be written in this form? Can, Follow me, right? Follow me. Don't be lost. If you're lost, come down later. I educate you can see 1,000 times until you get it. So our coordinate x can be written as r cos theta. Y can be written as I of r sin theta. Okay, and this is what we call the polar form, okay, of a complex number. Okay, so with that, right? With that, okay, you will be introduced to your first form, okay, second form, which is the polar form. Okay, where your z, you can see that this is nothing but r cos theta plus I of r sin theta. And using Picasso, you can see that this is just your y, the imaginary part, this is just the x, the real part. Okay, children? Can you all very quiet, very good. I think you're listening now. Okay, so this is the polar form. Okay, this is the polar form. Okay? Can how about the exponential form? Okay, the exponential form, right? Okay, there is a part which I really need you to. You can see the proof. Okay, there's a part I will need you to so-called accept it. Okay, the proof is actually done using power series. Okay, the proof, right, of the Euler's formula is actually in your comprehensive notes. Okay, it's in your comprehensive notes. Okay, it's done using power series. Basically, they use the power series of cosine, sine, and exponential. Okay, so you can actually relate to the proof. For now, this lesson, regardless of whether you read the notes or the comprehensive notes or not, I need you to take this as it is. Okay, I need you to accept this. Okay, accept it willingly and wholeheartedly. Yeah. So this is the Euler's formula. Euler's formula will tell you e to the power of I theta is equals to cosine theta plus I sin theta. Okay, this is the Euler's formula. I say again, the proof is in your comprehensive notes. Okay, so go and read it up. Okay, using the Euler's formula, okay, we can actually express our polar form into the exponential form. Okay, because, let me just write it. Z equals to R cos theta plus I sin theta. Okay, using Euler's formula. Okay, so you can see Euler's formula will tell you this is equals to e to the power of I theta. Okay, this is nothing but Euler's formula. Okay, so therefore the exponential form is just R. I replace this with e to the power I theta, and this will be my exponential form of a complex number. This will be the exponential form of a complex number. Okay, the proof is simply by Euler's formula. Okay, children, this will be the third form. What about your R? You can see that there are some things, the old friends, right, that they will never leave you. That is your R, your theta. Okay, your argument, your modulus, they never leave you. That is why on Monday I took so long to introduce these two friends to you, because they will stay by you throughout the whole journey. Okay, there's R and theta. One is your modulus, one is your argument. These two good friends you must go. Okay, cannot find them, don't have friends with. Okay, so must have these two. Okay, one is your argument, one is your argument. One is your modulus. Okay, so there are a total of 3 forms: Cartesian, polar, as well as exponential. Okay, and with that, question 15 was presented to you. Question 15 is there. The solutions are there. Stop talking. The girl holding the. Okay. So very quickly, this is the Cartesian form. Okay, this is the Cartesian form. Okay, no more. Okay. This is the Cartesian form. Then this is the polar form. Okay. Right? So you can see that what is the argument of 3? Argument of 3 is just 0, right? Okay? Argument of is just 0. What is the modulus? The modulus is just 3. Okay, so remember your two friends. What is the modulus? What is the argument? They must never leave you. Okay? The modulus R, the argument 3 pi over 4. Okay, I assume you know how to find this out. Okay, you know how to find the two friends, right? Argument and the modulus. Again, R e to the power of I theta. This is the argument. Okay, this is your modulus. Okay, 1 minus I again. This is your modulus. This is your argument. Okay, this is your modulus. Alright? Can, so this is for your, this is why question 15. Question 15, the basic idea is to get you to be comfortable in switching from one form to the other. Okay, polar to exponential, exponential to Cartesian. Okay? Can, okay. Any question? Okay. Okay, then question 16. Okay, for question 16, A, B, C is actually left empty. Okay, so I'm going to go through A and B very quickly. Okay, Z1 is equals to negative 1 plus I. Z2 is equals to 1 minus square root 3I. How do we find Z1 and Z2? So here, right, okay, let's try doing this. Okay, we imagine if I'm going to do this, right, okay, if let's say today as of now, stay with me. Okay, let's say today as of now, I haven't learned the polar form. I haven't learned the exponential form. Then I only learn the Cartesian form. What am I going to do? Find Z1, Z2. Okay, leaving your answer in the form of R, E, I, theta. That means I need to take some time to find the theta, right? I need to take some time to find the modulus, right? So, imagine, okay, Z1, Z2 I think is still okay. Okay, so imagine if I take Z1 multiply with Z2, I need to take negative 1 plus I multiplied with 1 minus square root 3I. Then for this, I need to find the modulus. I need to find the argument. Is it easy? Is it easy? Not really, not very easy, right? Not very easy, right? But, so try, okay, children, you can see what did they do? They actually express it in the exponential form. Okay? So moral of the story, if you forget everything I say, or if you're talking to your boyfriend and girlfriend during lecture, remember, okay, you see powers here, can you see? Here, right? One simple way of finding it fast is I express it in exponential form. Okay? Because here the question requires us to express it in exponential form. So this is ZR, this is Z1, exponential form, this is Z2, exponential form. From there, you can actually just combine. Okay? You can actually just combine. So you can see that you can actually see that if this is Z1, this is so-called R1, this is theta 1, this is R2, this is theta 2. Okay? And what is over here? This is nothing but R1 multiplied with R2. This is nothing but theta 1 plus theta 2. Okay? Can, right? So in general, that's the case. Okay, if you were to multiply so-called Z1, Z2, alright, this is nothing but, given that Z1 is R1 e to the power of I theta 1, okay, Z2 is R2 e to the power of I theta 2. What is Z1 times Z2? It's just nothing but R1, R2 e to the power of I theta 1 plus theta 2. But we have to be careful. Okay, later I'll tell you why we need to be careful. Okay? So basically when you do a product, is the indices, right? The indices are your arguments, the index are arguments. We just sum the arguments together. We multiply the modulus. Okay? So here, don't sleep, don't sleep. Okay. Okay, so here you can see that Z1 multiplied to Z2 modulus is the same as Z1 modulus multiplied with Z1, Z2 modulus. Okay, so for two complex numbers, simply put, the modulus of the product is the same as the product of the modulus. Okay, I say again, the modulus of the product, the modulus of a product is equal to the product of a modulus. Okay? And here, the argument of a product. So the guy is sleeping, right? So the two girls will stand up. Okay? The two girls will stand up. Come, the two girls will stand. Stand like that. The two girls will stand like that. Really, really. I mean it. Come. The boy will sit down. The two girls will stand. Quickly. Stand like that. Okay, so the argument of the product, the two girls will stand. The boy will sit down. Hey! You go and sit down. Sit down. Sit down! Okay, so this is for part A. Okay, so part A, I want to focus on one thing. Okay, equal sign. Equal sign. Why is it equal? Okay, look at part B. This is not equal. This is equivalent. Okay, why? There's a difference. There's a difference. Okay, there's a difference. Okay, this is equal. Okay, because if you observe, right, this is theta 1 plus theta 2. Okay, 5 pi over 12. Is 5 pi over 12 in a principal range between pi to negative pi? Between pi to negative, follow me, between pi to negative pi? Yes, right? Okay, but if you look at part B, okay, part B, right, Z1 over Z2, okay, the two girls, please take your seat again. Okay. Okay, if you look at part B, Z1 over Z2, okay, okay, so again, this will be R1 over R2. This will be theta 1 minus theta 2. Okay, but if you have theta 1 minus theta 2, right, this is 13 pi over 12. Okay, theta 1 minus theta 2 is 13 pi over 12. Okay, so after our arithmetic operation, we look at the theta. Is the theta in the principal range? Yes or no? Yes or no? No, okay, very good. You're with me, follow me. Okay. Then, what we need to do is we need to convert our argument back into the principal range. Okay, so we need this to be between, we need to check theta must be within pi and negative pi. Okay? Must be between pi and negative pi. Okay, so that's why it's an equivalent sign and we convert our argument back to the principal range. Okay, back to the principal range. Okay, so what do you observe in part B? The modulus of a quotient is the same as the quotient of the modulus. Okay, the so-called, if we take the modulus of Z1 over Z2, it's the same as we mod Z1 then divide by mod Z2. Okay, so the modulus of the quotient, the modulus of the quotient is the same as the quotient of the modulus. Okay, the argument of the quotient is the same as the subtracting the arguments from each other. This is like quotient law. This is like quotient law. Okay, right? Okay, easy, right? It's very easy one. Okay. Alright, okay, so with that, right? Okay, can you just take a while, look at part C? Oh, sorry. Should I show you? Okay. 3 minutes, let's do part C. Give me a while, I'll charge. For example, this is not, we find that after doing, this is a result of theta 1 minus theta 2. We find that our answer is not in the principal range. Okay, what can we do? Okay, how do we convert this back to the principal range? Okay, one very layman method, you don't say I say, but just like you minus, you keep minusing, minus 2 pi, minus pi. Okay, minus pi or plus pi, until you get the answer to be within, so we need this, right, to be between pi and negative pi. Okay? Another way to go about doing this, okay, is that I just draw it out. I just say, 13 pi over 12. It should be somewhere here. This is 0, right? This is pi over 2, this is pi. So 13 pi over 12 should be somewhere here, correct? But where is the argument? The argument is actually here. How do we measure this? Since from our diagram, 13 pi over 12, it should be negative. This one should be negative 11 pi over 12, right? Okay? Can all? So that's how we find the principal argument, okay? And when we do that, remember, it's not an equal sign, it's an equivalent sign. Okay? If you change, you must write equivalent sign, not equal sign. Okay? So I will go to 16C. Okay, 16C, right? If you were to do z1 to the power of 3, z2 to the power of 5. Okay, so the idea is if we try, we go and do this, we go and put negative 1 plus I to the power of 5. We put 1 minus square root 3I to the power of, to the power of 3. Answer to the power of 5. This is z1 power 3, z2 power 5. And if I do this, is it easy to expand? No, right? It's so disgusting, right? We did one example, it's like, wow, binomial, then how to do, wow, go crazy. Okay, but if we actually change it into the exponential form, oh, that is so nice, right? It's so beautiful, correct? Because we know that, oh, z1 to the power of 3. If your z1, if z1 is equals to r1 e to the power I theta 1, what is z1 to the power of 3? This one will just be r1 cube e to the power of I 3 times theta 1. Okay, so basically we just the power 3, okay, we just product the modulus, okay, and we sum the arguments, right? So it will be so nice to do. Okay, in general, argument, so-called the modulus of z to the power of n is the same as the mod z to the power of n. Right, the argument of z to the power of n is the same as n multiplied, or summing argument of z n times. Okay? Can. And from here, right, okay, basically we just combine the two modulus, like the two friends, right? One is your modulus, one is your argument. You cannot forget these two friends, okay? Then this will be your summing up the arguments, okay? I add them together. Okay, so if I were to call this, okay, maybe this is theta 1, this is my r1, this is r2, this is theta 2, then this part will be 5 times of theta 2, this will be r2 to the power of 5, this will be 3 times of theta 1, right, this will be r1 to the power of 3. Is it very confusing? No, okay, so yeah. And this portion here, so I add them together. This portion here is nothing but r1 to the power of 3 multiplied by r2 to the power of 5. This portion here is nothing but 3 theta 1 minus 5 theta 2. Okay? Yeah. Alternately, you can also do this way. Okay. So some of you actually, I think some of you actually split up. You went to find two friends, right? So you went to find the first friend first. You went to find the modulus. Okay. Then you went to find the second. You went to find the argument. Okay, when you copy, make sure you understand. Otherwise, when you copy later, you go back, you don't know what you are writing. Make sure you understand.